Okay, so I'll put up the recording for tonight's one and also last Friday's one together. Because Saturday is my tuition marathon day. So I didn't do any work after tuition. Just need to let my brain chill, decompress. So I gave this as work. Not sure if you took them down, but also I asked you to sketch this graph based on the photoelectric effect. So this question is not really a photoelectric effect question. It's more of a maths question. And they're asking you to sketch a graph of Emax, so the maximum kinetic energy against lambda. This is your axis. Okay, so lambda naught is your threshold wavelength, which is corresponding to your minimum energy required, basically your work function, hc over lambda naught. Okay, and then when the photons have a wavelength of lambda naught over 2, if you think about your E is equal to, or rather energy of photon is equal to work function plus Emax. And if we just base off their information, right? This is the first one. When energy of photon is equal to work function, Emax is 0. So when energy of photon is hc over lambda naught. So for this to happen, okay, maybe I shall do a table here. Build table. What graph should have table? So this is the value of lambda. And then here's the value of Emax. So from here, lambda is lambda naught. Okay. And then it says lambda over 2. Okay, lambda naught over 2. So if lambda is lambda naught over 2, the energy of photon, which is now equal to work function plus Emax, this energy of photon will be hc over lambda naught over 2. Okay, so remember that the energy of photon is equal to hc over lambda as well. So when this lambda is lambda naught, the energy of photon is straight away work function Emax is 0. We can actually plot this point 1. Lambda naught Emax is 0. This is the point. Okay. Then when this is hc over lambda naught, you know your work function. This is still hc over lambda naught. This is Emax. So from here, you can actually calculate your Emax because this is 2hc over lambda naught minus hc over lambda naught, because I can bring this 1 over 2 and throw up. So this is my new lambda. Okay. And from here, I will get my Emax as 1 hc over lambda naught. Okay. And it says here, when it's lambda over 2, the Emax, this is Emax. Okay. So lambda over 2 here is 1 Emax. And why did I do all this back-end work, although I can obviously plot this point just by reading the statement up here? It's because later on, they want us to actually find or the variation from lambda naught over 3 to lambda is lambda naught. So I can sketch the curve, I guess, or a straight line, I don't know, from this point to this point. But I sort of like need to know what is going on between here and here. So I need to repeat the process, but now my lambda is lambda naught over 3. Okay. So this one is Emax. Okay, continue the story. Lambda is lambda naught divided by 3. So just based off this equation, and this one that I have here, will be 3 hc over lambda naught minus hc over lambda naught. Oh, miss, how you know? Well, this one is lambda naught over 2. The 2 is here. And then after that, you multiply, you bring up. So it's 2 lor, this is the 2. Now you substitute with 3. So the same thing, the over 3 here will be kicked upwards because it's over lambda naught over 3. Okay, so let's skip a few steps. If you need to, then you slowly write. That is also okay by running out of space. So this one is equal to Emax, or rather the new Emax. I'm just going to call it Emax prime. Okay, so this one is 2 hc over lambda naught is Emax, right? Which means this new Emax is equal to 2 times the old Emax. This one is 1. Okay, or maybe I'll substitute for you. So this hc over lambda naught can be substituted here. So the new Emax will be 2 Emax. So when it's lambda naught over 3, you are dealing with 2 Emax. This lambda naught over 3 is neither here nor there, but it's this one. So just based on these 3 points, right, I already know I should join the curve, right? Because there's no way you can draw a straight line that connects these 3 points. So just in a smooth curve, draw like this. Must you pass through all the points? Yes. It's not an asymptote now. It will cut through this point. Okay, that's your graph. That's how you know lambda naught over 3 is for 2 Emax. You should change the color to correspond with the calculation. Lambda naught over 2 is Emax. Lambda naught over 3 is 2 Emax. Of course, you need to minus by hc over lambda naught first. Okay. Let me go find the mark scheme. But normally when it comes to this kind of graph, don't leave empty lah. There's always some marks to get, even if you can't manage to plot the last point. Okay. So it says here, if you have a line with negative gradient, you get 1 mark. Now, negative gradient. A line passing through lambda naught 0. You definitely can plot this point because this point is given here. So whenever you see maximum wavelength, this is threshold wavelength, Emax is 0. Okay, threshold. So curve with negative gradient of decreasing magnitude. Yep, there's a curve passing through half lambda naught Emax, this point, and 1/3 lambda naught 2 Emax, this point. So even if you can't find the points, as long as you draw the right shape, you should be okay. And you should know the first point just by inferring the idea of threshold wavelength, because threshold wavelength is related to minimum energy. So I use up all my energy already, and I have no more energy left for maximum. Okay, so what we're doing is we are changing the light, different photons. Okay, lambda is your variable. So you have different lights of different energy. So when we are talking about the longest wavelength that can allow photoelectric effect, it means that all the photon energy is used up. Not much is left. All right. But in other words, this one is just calculation. So just that case using the equation, substituting the conditions in to find what Emax to plot. Okay. All right. Let me know if you're okay. I'm gonna do some other questions that is related to this one. Okay. So photoelectric effect in a nutshell, right, is just us showing wave, which is your EM photon, electromagnetic photon, behave like particle. And the so-called particle behavior is not because it has mass, but because it has quantized energy. So the energy is discrete. For example, your energy is discrete. Your energy is contained inside your cell. Your energy is not outside of your body, it's inside of your body. Okay? If I have a ball that is moving towards you at 2 meters per second, the energy, the kinetic energy of the ball is inside the ball. It is not around the ball. It is not next to the ball. It's inside the ball. So we know very certain, oh, this is where all the energy is located. This is a ball, oh, traveling at 2 meters per second, 1 kg ball. So I'm very sure the kinetic energy is here. The kinetic energy is not here, not here, not here, not some random place here. And light is supposed to be continuous, which is as long as we know the wave source, we know that light will travel in all directions. It sort of spreads out, right? So what this EM photon does is that it rejects this model entirely, and it says that sometimes light can be wave, but under certain conditions or under certain experiment, the only way to explain what is going on, like the photoelectric effect, is for light to change into particles. So the energy is like now fixed in a quantized format. Okay. And the reason why we know this, or what is important for this, is number one, to be able to write out the observations. Okay. Number two, to be able to define things like threshold frequency, threshold wavelength, work function, and stopping potential. Okay. And finally, using the equation, energy of photon is work function plus KE max, to do calculations and do graphing, because this is just a study of an experiment. Okay. So this is the photoelectric effect. The next one that we're going to do in quantum physics is to answer the question, if light can behave like particle, can particle behave like light? Can I mash it up together? Is there some duality? Well, I'll say yes lah. Okay, so the line between particle and wave has begun to blur. We are sort of like close to the threshold of physics already, but I want you to understand, today we're going to look at the wave-particle duality. Duality means both also can. Dual. All right. So in the last class, we talked about the photoelectric effect, which is light behaving like wave. Okay. So particle behavior means that the light have something like quantized or discrete energy, and or we can also say it has momentum. Interesting. Okay. And today we're going to look at this experiment called the electron diffraction, where we have particle, which is your electron, exhibiting wave property. So the wave property that comes to mind is something like diffraction, which means what we should be able to calculate, because anything that has a discrete energy will have momentum, like the ball rolling towards you. Okay, so anything that's diffraction, will be able to have wavelength. So we're going to look at how to tie momentum and lambda together. So this is the setup. All right, what we have is a good old electron gun that we will accelerate and whack it against a graphite target. Wow, scientists like to accelerate particles and collide with stuff. You're right. That was what scientists did for the earlier of the 20th century. Alpha particle against gold foil, electrons against graphite target. Nice lah. Scientists, it was fun. It was just throwing electrons at a target. Okay. So before we encounter the graphite target, the electron gun, the electrons that come out, right, they show particle properties, meaning they're like a particle, like we visualize them to be, and they can actually collide with something. But when it passes through the graphite target, right, inside your thin graphite target, you can imagine, let's say this is your layer. There are many, many tiny atoms, and the atoms, they don't touch. They're not supposed to, because, they have orbitals, and their orbitals are all negatively charged, So they're going to have gaps between the atoms. And when the electron passes through the gap, something strange happens. The electrons begin to like spread out. So weird one. Why will spread out one? Okay, let me show you how it looks like when we simulate it. Now, you can listen to sound if you learn better with sound. Yeah. You know what? I'm going to share the link here. You can watch it later with sound. Because once I play sound, they're going to copyright the question. Apparently, you cannot view your class recording. And then I will be like, I don't know how to change that. Okay, I'm going to mute. All right. So right now, what we see here, okay, is a wave pattern. This is what we expect particles to happen, right? You shoot a bunch of electrons to two holes and okay lah, at the hole there, but the electrons sometimes langgar tepi will sengek sedikit, but we don't see any pattern, it's just random simply anyhow. But if a wave passes through two slits, we all know what happened, right? We get the interference pattern. So just now when particle passes through slit, no pattern. But when wave passes through slit, we get interference, bright, dark fringes. Okay, because everything here, constructive interference, you can see all the nodes. This is your nodal line. Then here is your antinodal line, this part here. So you can see, you can get all these bright and dark fringes. But let's send a quantum object like an electron. This cloud of quantum object will collapse into a particle. So that means when I hit the graphite target, because the graphite target is not just two slits, it's many, many slits because you got many, many, many atoms with many, many gaps. So once they pass through the first layer, they will begin to behave this kind of this, and then they collide. So as we repeat this repeatedly, we got interference pattern. But now we're going to let you stare at it. And you know what happens when you stare at your quantum object? They become a particle. Hello. And then suddenly this one have no more wave behavior already. The electron will go all over the place. So you looking at it caused the electron to change behavior. Teacher, why so weird one? Welcome to the world of quantum physics. Okay, let's recap. When a particle passes through a gap, two gaps like that, There's no pattern line. It's just going to spray all over the place because they will collide with the wall, they'll collide with the side of the wall, they'll collide with each other, and then just spray all over the place. This one all no problem. This is just daily life. You know, lepas stress with throw stuff. Okay. A wave, when it passes through two slits, we sort of know what happens. We get fringes on the screen. Bright up, bright up, bright up, bright up fringes. Okay. What we're studying now is a quantum object. So what is a quantum object? Example, an electron is a quantum object. Okay. And we only look at the electron for now in your syllabus. So this electron, which I'm going to pause here. And if you're wondering, teacher, why the electron is this? Why is this? This is the electron cloud. We call it an electron cloud, like R1. So if you think about how you define orbital in your chemistry, it's a region of space where there's a high probability of locating an electron. So there's a high chance of you finding an electron. That means this region, high chance to find electron. That means we don't know where the electron is? Nope. But we know where there's a high chance to find the electron. Just like I could say that, oh, I can map out your cloud, Xiao Wei's cloud, and probably is in her room, in class, in the toilet, the canteen. Places to find this person, okay? Places to find the electron. But as the electron travel further, the probability become more and more. And then I don't know where the electron is, Is the electron here? Is the electron here? Is the electron here? Don't know. The darker the color, the more likely it is to find the electron. But actually, we don't really know where the electron is until we hit the wall and we know the electrons, all the possibility collide to one point. All the possibility of the position of the electron collapse to one point. So this is what they mean by the wave reduces into a particle when touching the screen. Okay, so it's a bit like you can now you can be anything you want, right? You can be teacher lah, lecturer lah, accountant lah, go in the bank lah, insurance agent lah, a viral TikToker lah. You got endless possibilities. But once the time comes, all your reality will converge into one. You are whatever you choose to be later lah, but there's only one reality. So the same thing as this one. The electrons sort of like collapse to a position when they reach a barrier. So we get that bright up fringes, which I will shall pause for you to see a bit faster. You can see the bright up fringes, which looks a lot like this bright up fringes. Okay. But the strange thing happens is when you go and add an observer here, you go look at it. Hey, why does electron behave so weird one? You go look at the electron self-conscious, or the electron will behave like a particle. It will lose its wave property. Now, why is that? We don't know. We just know it behaved like that. We don't know why it behaved like that. So there's no interference. The observer, the act of you looking at something has changed its property. Hello, your brain, okay. So welcome to wave particle duality, aka quantum physics, aka what is going on? Okay, so today's idea is because of this behavior, and if we do this inside an electron bulb thingy, we can actually observe this behavior. But what we're observing is not the actual simulation that I show you, but what we get is a setup that's something like this. Okay, so we will see concentric rings because we're passing it through a graphite target, and then instead of bright dark lines, because the graphite target is 3D so it's going to form rings, bright dark rings. Okay, another close-up of this would be something like this. Okay, so what we have is a bunch of electrons, and the graphite target allows us to create these kind of gaps where the electrons can pass through, or slits. And then once the electrons show wave property, you will get diffraction rings spreading out. If not, all the electron will just, there's no pattern, it's just all over the place. Okay, so yeah, what do you need to know? Well, we don't derive the equation because it's just going to freak. The derivation is very long. I told my university lecturer like 1 hour to derive the equation. We just use the equation, no need to derive. Okay, so we're going to use we're going to do some calculation involving wave particle duality by using de Broglie's wavelength equation, where lambda is equal to h over p. Okay, so let me define everything for you first. Lambda here is a wave property. So this lambda is known as de Broglie's wavelength. I know the Malaysia, we want to pronounce all the vowels, so we want to de Broglie, but it's de Broglie. French punya pasal. So the de Broglie's wavelength. Okay, lambda. So this lambda is to show us a wave property. Okay, can be diffracted, can undergo interference. Okay. And this momentum is a particle property. Momentum, particle property. And this h here is your good old Planck's constant, the one that we used in the last class. 6.63 times 10 to the power negative 34 joules second. Okay. When we use this one, everything is SI. I just want to kindly remind you that, you know, momentum is mass times velocity. So this mass here would be mass of electron, and velocity will be the velocity of electron. But means how to find velocity of the electron? Sub-equation number 2. I can say that the kinetic energy of the electron is equal to work done by electric fields. So the work done by electric field is QV. And this one is half mv squared. But we're talking about an electron, so this is mass of electron, particular mass of electron. Okay, this Q would be electronic charge. And this V here is accelerating potential. So if we go back to our drawing, this one here, my accelerating potential is applied across the electron gun and the graphite target. So between here to here, I will accelerate. Basically, I just make this one very positive by connecting to a power supply. Okay, fine. Connect to a high voltage power supply, many battery. Okay, so here is your V, your accelerating potential. Okay, so based on how fast I hit the metal target, I will get wavelengths. And because wavelength is a wave property, I expect to see diffraction rings. And we like to call this pattern, or at least your syllabus calls this pattern, concentric rings. Concentric because they share the same center. Okay. So again, we have electron gun, and we bombard or accelerate towards a thin graphite target inside an evacuated tube. Teacher, what's an evacuated tube? That one is normal glamour for vacuum. Evacuate means to remove, right? Oh, evacuate the building is a fire drill. Okay, remove people from the building. So to evacuate a tube is to remove air from the tube, vacuum. Okay, and then later here we will observe diffraction rings, and normally when you can see this kind of green color one, I don't know whether you remember or not, it actually means that this side here we will salutkan, we'll paint with fluorescent paint. So here would be some fluorescent screen. So that when the electron collide with it, it will glow green color. Luminous. All right. So as you can tell, right, depending on the type of accelerating potential, low V will get the rings further apart, and high V will get the rings closer together. So if you're wondering why, right, we can actually tell from the equation here. Okay, so I'm going to briefly mention the effect of accelerating potential. Well, number one, as V, okay, let's say V increase. Accelerating potential, capital V increase. I can say the velocity of the electron colliding with the target metal increase. And because of this, number two, I can say momentum of the electron also increase. Of course, you know, P equal to mv, larger V, larger momentum. Okay. So if the momentum increase, P increase, then I can conclude already, because from your brand spanking new de Broglie equation, when momentum increase, wavelength decrease. Okay. Wavelength decrease, this means there is less spreading. Which tells us that the rings are closer. Sure, what means less spreading? You see, you see. Last time in your AS, condition for diffraction is lambda must be more or less equal to gap size, or D. Okay. And also we will say things like when gap size decrease, more spreading, when lambda decrease, more spreading, sorry, less spreading. I think the best way I can help you settle the headache is to just use equation. Remember, d sine theta is equal to n lambda. So from this equation, when lambda decrease, I can't change the atomic spacing of my graphite target, right? I can't I tell the graphite atom, hey, move closer together, please, not possible, right? So everything else is constant except my angle theta. So when lambda becomes smaller, sine theta will have to follow. Sine theta becomes smaller, theta becomes smaller. So if you remember your diffraction equation, theta, let's say this is the bright line, this is another bright line. Here to here is your theta, right? So if your theta becomes smaller, the lines are closer together. So theta decrease just means the rings are closer. So sometimes they will ask you, oh, the accelerating potential is increased or decreased. What happens? So of course, this one is what happens when it increases. When it's decreased, you just everything reverse the explanation. Okay. So that's accelerating potential for you. But in a nutshell, right, you can see this whole experiment as how I'm going to show you a bunch of memes. First one is very meme worthy. The photons are both waves and particles. And at the end of the day, right, we can actually represent particle and wave. We need both. There's no such thing as, so is electron a particle or a wave? The answer is both. Both at the same time. You need both to properly describe electron. Because, for example, I know that the wave property here is number one, it has mass. So it must have momentum. So on one side I have P. Okay. And then on the other side has wavelength. But teacher, wavelength of electron, correct? Electron got wavelength. Teacher, does it mean that I have wavelength? Yes, you also have wavelength. We can calculate your wavelength also. We just need you to have some momentum. Okay? So on here you have lambda, or rather, let me just insert a constant h over lambda. Okay, this was the equation that we're using. It bridges these two physical properties that used to be a close divide. Okay. And the other thing about particle is that you know where the particle is known position. For example, you know where you are now. I'm sitting in my room on my chair. Yeah. So if I know where you are, I know where your energy is. So because of this, we know the position. Energy is quantized or discrete. So this one is when there is the photoelectric effect of light, EM wave. So light or EM wave already begin to show particle property. But for this lambda, as mentioned just now, the 2, it can be diffracted. Okay, so just a reminder, what is diffraction? It's a spreading of wave as it passes a small gap, forming a geometric pattern, like a concentric circle or bright dark fringes. Okay, so this particular thing, experimental wise, your electron diffraction, this is I'm going to write the experiment, electron diffraction. So we actually have proof or experiments to show both at the same time. Interesting. So we actually need both in quantum physics. Particle behave like wave, wave behave like particle. My life is a lie. No, your life is not a lie. Just new stuff. Okay. Also, one last thing before we try out some questions. You may be thinking, last time I heard of this microscope. Very OP, they call it the electron microscope. Is it because they found a way to diffract electron? Yes, this is the electron microscope. Okay. The cool thing about the electron microscope is that, instead of a normal optical lens, and you remember last time in high school for the optic chapter, you had to draw all the light rays or not? To remember the lens, telescope lah, microscope lah. So this one is nicer because it's not light, it's an electron. So we know a lot of stuff about the electron. We know how to set up an electric field. We know how to set up a magnetic field. We can manipulate the electrons way better than we can manipulate light. Right? Light also can lah. Humans are pretty cool already. We got mirror, we got lens, but nothing beats the fine tuning of an electron. Because electron means can plug into the PC. Okay. So what we can do is we'll just place a sample and we'll pass it through some magnetic lens. And the main pros of an electron microscope is the higher resolution. Because the wavelength, no need to copy, no need to know. You just need to explain why we like this. The wavelength of electron is less than the wavelength of visible light. Okay. Hence, since lambda must be more or less equal to the gap size for good diffraction pattern, and the atomic separation is around 10 to the negative 10 meter, a shorter lambda electron allows greater resolution, which means I can see, I can zoom in more, allows smaller structure to be seen. High res, higher resolution or greater resolution. So that means I can actually, this one I can see smaller stuff compared to a regular microscope. So after the jump, I'm going to show you some scanning electron microscope images, which is very nice. I heard they're quite expensive. And like one university can only buy one. Okay. So they are normally very chunky because we need a lot of circuit to control the field. But you don't really need to know how the insides work. I just think it's really cool because, see, this is going to be small, but you can use lens or instead of using glass lens, like light, like what I'm wearing the glasses, I can use electricity to control, which is very cool. And you'll be wondering how the image look like. Well, this is an example. Okay, this is pollen. What is pollen? The bunga. The flower, the the flower pollen. So all these sharp hooks will tie to your fabric or tie to the mammal's body. Mammal got hair, mammal is hairy. So they hook onto the mammal's body and the mammal helps carry the pollen around the world so that other seeds may get germinated. Okay. So this is an example of the sticky residue on a post-it note. You stick the post-it note, belakang got glue, right? This is the glue. Okay. So I like to look at SAM images, for bacteria and virus because all these bacteria, it gives you nice images. This is algae. I prefer to look at the tardigrade. This is a tardigrade. So what's a tardigrade? A tardigrade is inside all water. This thing is in the water that you drink. It's fine. You'll be okay. Just don't get nightmares. Okay. Okay. So these are all different cells. It's kind of cool. This is Velcro, I think. This is obviously red blood cell. They helpfully color it red for you to look at. So this is a rabbit hole, my friends. This one looks very fake. These are all rabbit holes. Something that you may learn last time when you were in high school, especially if you study bio. This is the good old bacteriophage. Remember or not? You learn this in bio the bacteriophage inject the RNA and then the RNA take over the DNA of the bacteria. Then the bacteria explosion. Then got many bacteriophage. So we can actually observe this in the microscope. This is the bacteriophage. Okay. So we do need a very OP microscope like the electron microscope. This is obviously color coordinated, but this reminds me of a creeper in Minecraft a bit. But anyway, bacteriophage. Okay. So scanning microscope is very cool. This is your hair, the keratin. It's basically, this is obviously sperm, blood cell. Yeah, it's basically a very nice rabbit hole that you can just dive into. You know what is this? This is split end. Your hair long, right? They will have like those knots. This is a split end. Okay. Scientists, so bio very fun one. You just slap some stuff under a microscope and stare at it. This is the trapped red blood cell, probably inside some what is the thing that cause coagulation one? They will color it so that you can see the difference. But yeah. Tongue. This on your tongue. This is your tongue. Wow. Okay lah. So you can go to town lah. Very nice one. You just want a chill night. If it's your thing. Your tongue. Okay. The tongue surface. You know why not? So there are a lot of receptors under these folds. If you eat something you're not supposed to eat, your evolved sense of taste will tell you to throw up so you don't poison yourself. Human body is an amazing thing, okay? Anyway, back to the physics. No more bio. I get the idea lah. I think de Broglie's electron microscope, by showing, you know, this kind of image, has really started something different for sciences. We are able to use this to create patterns and then to study the diffraction ring. If it can be diffracted and you have light behavior, you can use it to create microscope. Okay. The only part you need to know is just why is electron able to show greater resolution. The main idea is the wavelength of the electron is much lesser than the wavelength of visible light. All right, we're going to try some questions now. And I guess we will start off with something that is a bit more standard first before we carry on with slightly non-standard questions. So this one is in page 23. So I have to adjust the size a bit. Inside. Okay, page 22. And as you can tell, it's the same setup lah, okay? So it says here that electrons traveling at a speed v in a vacuum is incident on very thin carbon film. Sure, graphite is carbon. Emergent electrons are incident on a fluorescent screen. Beautiful. A series of concentric rings are observed. Okay, ring. Suggest why the ring provide evidence for the wave nature of particles. So you can say that the rings, or the concentric rings, are evidence of diffraction. And you can helpfully remind them that diffraction is wave nature, or diffraction is a wave property. 1 mark each. This is M1. That means you must score this mark first before you can get this one, A1. If you just start diffraction is a wave property, I'm like, yeah, I know but how does it relate to diffraction? Or rather, how does it relate to concentric rings? Okay. All right. B, the initial speed of the electron is increased. So the velocity of the electron increased. State and explain the effect, if any, on the radius of the ring observed. Okay, let's go through the process. If V increase, momentum increase, lambda decrease. Okay, so if you need equation, I write down here for you. P is equal to mv. Lambda is h over p. So when p increase, lambda will drop. Now when lambda drop, you can, theta will also drop. And again, I'll write the equation for you. D sine theta is equal to n lambda. Okay, so we'll just put all of it together and talk about the speed of electron. So you can say the momentum increases, momentum of electron increases. Then you can say from lambda is h over p, wavelength of electron decreases. So if wavelength of electron decreases, then there is less spreading of the pattern, the diffraction pattern. So the radii decreases. Okay. So momentum is m1. Wavelength of electron decrease is m1. And this radii decrease is a1. So use the equation. 1 mark is here, 1 mark is here, 1 mark is here. Okay. Less spreading, radii decrease. Okay. So moving on to the calculation portion. Okay. There are two calculations that are very similar. So I'm going to do one, and I'll let you do the other one while we also go for a short break at the same time. So here we have a proton and an electron accelerated from rest through the same potential difference. Okay. Can proton be a quantum object? Can. Anything now can be a quantum object. It's just whether the wavelength makes sense or not lah. Like if let's say you are running, or let's say you are sitting in a car, let's find the wavelength of human. You are in the car, right? 6.63 times 10 to the power negative 34. Your mass is, let's say 50 kg. Let's say your car is traveling at 10 meters per second, which is kind of slow, around 36 km per hour, 40 km per hour. It's like the KL jam traffic lah, okay? Teacher, this one, your wavelength is going to be something times 10 to the power negative 36. I don't even know what this is. What is negative 36 meter? Like your wavelength doesn't matter, it doesn't exist, it's too small. There's many zeros, okay? So for this wavelength to actually mean anything calculation-wise, I need the momentum to be really, really small. And the only way for the momentum to be really, really small is for things to be like proton and electron. So you may be thinking, well, miss, if I'm like wave and I pass through a gap, I can get bright, dark fringes. So I can create many clones of myself and each person can go and do one thing. I'm sorry to say, unless we can decrease your mass, your wavelength. How to make a gap size this big? What is a gap size this big? So the wavelength is too small. But particle one are all okay, no problem. All right. So they're asking for lambda p over lambda e. And you might be thinking, well, I know h is lambda is equal to h over p. So I can write this as the momentum of electron divided by the momentum of proton. Because of the inversely proportional. However, to find momentum, I will take the mass of the electron, velocity of the electron, over mass of proton, velocity of proton. Now, just because they have the same potential difference doesn't mean they have the same final speed. So I need to settle what is the ratio of the speed first. I know the ratio of mass, no problem, but I need to know the ratio of speed. So from here, I'm going to find the ratio of VE and VP. I can say that the change in kinetic energy is equal to work done
by electric field. So the change in kinetic energy, which will always be from rest, if not, the equation cannot ratio nicely. This will be half mv squared from rest minus 0. And work done by electric field is QV. But this is an electron anyway, so this is E. So what I have now is V squared is E 2 EV over M. And then I feel there are many constants here. For example, 2 E and even same potential V are constant. So finally, I will have velocity square is proportional to 1 over M. So if velocity is proportional to 1 over M, and I want to find VE over VP, this will be MP over ME square root. Because the V square I bring over and square root. And the 1 over, I will flip the ratio. That's why it's 4 marks lah. You need to do hardcore ratios. Ratio is your best friend. So from here, I can substitute. Lambda P over lambda E is ME over MP bracket MP over ME power half or square root. Teacher, can bring it into the same square root? Can just multiply then? Can. I prefer to bring it into the same square root lah. So lambda P over lambda E will be equal to big square root. This is ME square over MP square. This is MP over ME. So at the end of the day, I am taking square root of mass of electron over mass of proton. And I can now substitute the values. This will be 9.11 times 10 to the power negative 31 kg. This one can copy from your page, front page data sheet. 1.67 times 10 to the power 27. Power half or square root. And this will give you 2.33 times 10 to the power of negative 2. Another method is, I like to use ratio because I can very quickly throw away constants. Like all these 2 EV, no need to see already. If ratio is not your cup of tea, let's shrink a bit so I got space to write. I'm gonna give you an alternative. Depending on your maths, like how do you normally solve questions like this? So at the end of the day, what I want is to have an equation of lambda and mass of electron and proton. The other things I want to eliminate because I don't know. I don't know what the potential is. I don't know. I only know the charge and the mass. So for these two particles, right, the only known things is Q, which is the same, different polarity, but same magnitude, and M. I don't know what is this. They didn't give me. I don't know the wavelength because I don't know the speed. So I also don't know. So I'm going to start with this one. P is equal to H over lambda. I can handle P because I know the mass, but I don't know the velocity. So MV is H over lambda. I want to keep lambda here because they are asking for the ratio of lambda. Okay, so I choose what I want to keep. I want to keep this one. I want to keep this one. So now my modus operandi is substitute V. Okay, so to substitute V, I'm going to use this equation. So I have V squared is 2 EV over M. Okay, then I put inside M bracket 2 EV over M whole thing square root close bracket. This is H over lambda. We do some simplifying. Okay, this is 2 EV. And then you bring the M inside, is M square, right? This M square I put here. So what you have left is square root of 2 EV M square. Is H over lambda. Now you can kick away the constant law. Because at the end of the day, where's my, why do I have M squared? Sorry, 2 EV over M. The rest is constant. So from here, root M is inversely proportional to lambda, which was what we did here. Now, also can, up to you. To me, they're the same, but you can obviously substitute like this and move things around. It's just substitution. So to give you, to let you have a better sense of this substitution, okay, or rather the steps required to substitute, as usual, numbers are easier for the brain, rather than knowing what to eliminate and knowing what to keep. So when I started this, I know I'm going to use this equation. Momentum is H over lambda. I chose to keep M and lambda because I know the mass of electron and proton, and I want to find the ratio of lambda. H, I don't care lah. It's a Planck's constant. I divide, they'll go away. Doing ratio. So I need to substitute V. And in the process, once I substituted V, I can nicely throw out all the constants, which is 2 EV and H, leaving root M as proportional to lambda. 1 over lambda, or lambda proportional to 1 over root M. Then I can just solve using ratio. 4 marks. You may be thinking, where's the mark? Well, very easy one. CIE mark scheme. The mark is this one. If you write this, you get 1 mark. Okay. If you use MV, use one color for this one. If you have MV, and then you have conservation of energy, you get 1 mark. So basically, you know you're supposed to find velocity lah, and put it inside a momentum equation. You arrive at this kind of square root one, you get 1 mark. Correct square root ratio. And then finally, the substitution and the answer is the 4th mark. Okay. Yeah. No problem. Hopefully. Take a breath. Okay. We're going to take a 10-minute break. Also for you to go and stretch a bit and then to try this one. So this was the old 4 mark. I think this is 2013. 2013? This is 2020. So let's take a look at more recent questions. This is the original full de Broglie question. Later, we'll take some de Broglie, I'll mix it up with some photoelectric effect, and we want to see how those questions look like after the break. Meanwhile, take a short break. I'll see you at 10:05. You go try this question now, okay? Go try this one. I zoom in for you. Where do you want the screen to be? You want the screen to be on the question? You want the screen to be on this one? Never mind. I throw both into Discord. Both. Wow, both. Sunny, how to both? Okay, never mind. I throw into Discord now. I put in the general channel. I don't know where to put. I think I should create a channel called class screenshots. So I'll put it in the general one because I need to go washroom. No. So there's the notes, and then it's the question. Okay. BRB. Come back at 10:05. Also go stretch. Discord here. I just jump out in the general channel now. You tak cukup besar, you can click open original. And then it'll bring you to this one. Yang besar-besar lah. So as long as it's there, you can always copy this image and paste to whoever you want to paste. It's the beauty of Discord. Okay lah, that's all. I'll see you. See you in a bit. do the crystal. BRB at 10:05. I'm going to stretch. Let me pause the recording.
Okay, let's go. Right, this one is nicer because they give you numbers. Okay, so we are going to study the structure of copper crystal using electron diffraction. And electrons being accelerated from rest for potential difference V are incident on the crystal. You are given lambda this time, the Broglie equation. Calculate the accelerating potential difference V. So, of course, you're like, sure, can I memorize this one? I don't recommend, because if you memorize this, not judging your memory, maybe you can. Where will the marks go? Because let me show you where the marks are. I won't know how to give you marks. Okay, so we need to start with, let's say you start with accelerating potential, or rather your de Broglie wavelength actually, because that one is what you have. And P is equal to H over lambda. You can find the momentum of the electron. Okay, you can look for it one by one, but I know that eventually I need to find the speed of the electron. Okay, so I'll do it step by step. 6.63 times 10 to the power negative 34 divided by 2.6 times 10 to the power negative 11. Okay. This one is 2.55 times 10 to the power of negative 23. Okay. And then you can find the speed of the electron. P is equal to mv. So 2.55 times 10 to the power negative 23. Mass is 9.11 times 10 to the power negative 31. Electron, right, times V. So you can find V now. 11 negative 31. This V is 2.799, 2.8 times 10 to the power of 7 meter per second. So values that they will give you in the formula sheet is these two. Okay, I'll write down here. H and mass of electron given in formula sheet, page 2, I believe, 2 or 3 lah, the front part of the exam paper. So we have the velocity already, but they want the potential difference V. So I can say that the electrons are accelerated by the potential difference V. So change in KE is work done by electric field half mv squared is equal to EV. So you can find V. V would be half mass of the electron multiply again. The reason why we cannot keep mv as momentum is because of the V squared. So no matter how, also you need to find V1. 2.8 times 10 to the power 7 square divided by E, 1.6 times 10 to the power negative 16. So, yep. This is negative 19. And I have 2230 volt, 2231.95. Okay. So normally the accelerating potential should be a few thousand. I know this because I've done enough experiments and questions, but this kind of accelerating potential difference is a few kilovolt. If you get like 0 point something, something is wrong. You either, like me just now, write the wrong prefix, and didn't catch yourself, or maybe you've forgotten to convert something. Otherwise, the calculation is very straightforward. So answer is 1 mark, right? If you find the velocity, you get 1 mark. You find the momentum correctly, you get 1 mark. So please show the working, okay? And then finally, if you use the electric field equation, change in KE is work done by electric field, get 1 mark. Of course, again, include the substitution. So if you straight away memorize the equation, by equation, I mean, what was it again? I derive here now. This one, if you memorize this one, I don't know how to give you marks. It's not wrong, I just don't know how to give you marks. How do I assign the marks for you looking for momentum? How do I assign the marks for correctly finding velocity? Don't know. So another student may not want to do all the intermediate calculation. Okay, they may think, I want to find potential. So half mv squared is equal to EV. But also at the same time, P is equal to mv. So, and also because there's only these 3 equations to play with, no? P is equal to h over lambda. I have lambda, so h over lambda is equal to mv, velocity of electron. V here would be m lambda over h. Throw inside, half m bracket m lambda over h is equal to EV squared. Also can, the answer will be the same. This will be m cubed lambda square over h square times E. But when you do this, I can see this one went into, because I'm looking for, student looking for momentum. So got momentum already. Okay, and then I'm looking for, hey, later on, you know, momentum is mv, and then you substitute v, you get 1 mark. This one is 1 mark. So if everything works out right, then you're okay already, because this will be half. You can try and see lah. Power 3. Wavelength was 2.6 times 10 to the power negative 11 squared. But I know the mark scheme. The mark scheme will look like the one that I showed you. And I always think about making my examiner's life better, because they mark a lot of scripts. I want them to like my script above all the other scripts. I just want them to have an easier time marking my paper. So even if I do this method, I'll make sure I lay down all the steps. Okay. I'll cry if this one is not the same. Also, I'm sort of like double checking. Power 3. Up to you lah. It's just a bunch of algebra. 11. I square b square. Sometimes when your number is too big, your calculator cannot handle. Because there are too many prefixes lying around. Let's what about this? Yep. Wow, my calculator cannot deal with the prefix. It's just error too. Okay lah, you stick to this one lah. This is fine. It's okay to just keep rounding to 2 to 3 SF along the way. I use the normal Casio calculator, not the Changi Mandu one. Yeah. All right, we're gonna carry on and look at some anomalous questions, because, you know, recently we have strange phenomena that we can use to describe this collision. I'm going to start off first by talking about pressure. Pressure. If light can behave like particle can exert a force, and force will have pressure. This one on the page. Ready? Like that. This one. Okay. So for this question, you are given a light of wavelength 590 nanometer, incident normally on the surface. Okay. The power of light is 3.2 milliwatt. Page number, this is page number 9. Light is completely absorbed by the surface. Beautiful. Calculate the number of photons incident in 1 second. So all I have is lambda and power. Power, P, not the Broglie momentum, okay? Power. So if I think about power, power is energy over time, right? And the time is 1 second anyway. So I guess this energy is the energy of photon. And this T here is 1 second. So I'm going to put in 3.2 times 10 to the power -3. That's my power. Energy of photon is equal to H. They give me lambda, so HC over lambda. HC over lambda. I guess if you want to, you can divide by 1. You only 1 photon. Impossible. You don't have 1 photon, right? You have multiple photons. I got 1 photon one. It's like, oh, there's 1 electron, my dude. To isolate out the electron is hard work, man. There's a lot of it. So simple. Multiply by n. Okay. So I guess we'll find n. N will be equal to 3.2 times 10 to the power of -3 multiplied by wavelength 590 nano divided by 6.63 times 10 to the power of -34. 3 times 10 to the power of 8. So speed of light is always given to you. -3 -19, -34. So I got 9.5, 9.49 times 10 to the power of 15. Okay, so energy of photon is Hc over lambda. You'll get 1 mark already now here. Okay. And then you use the equation power is energy over time. And you remember to multiply by n. This is 1 mark. Showing the substitution and the final answer is 1 mark. So it's always worth it to write the equation that you think is relevant, although you may not know how to use it yet. Don't leave empty, lor. Never leave things empty. Try. If not, the marks buang a bit sakit hati, you know. Okay, use your answer in A to determine the total momentum of the photons arriving at the surface in 1 second. Interesting. So what we're looking for is momentum of photon in 1 second. So P is equal to H over lambda, but this one is for 1 photon. We have n photons, so multiply by n. Of course, you can always find 1 photon first, no problem. 6.63 times 10 to the power of negative 34. Wavelength is 590 nanometer. Put line inside. And then you get 1.12 times 10 to the power of negative 27 kg ms negative 1. Hence, total momentum will be equal to 9.5 times 10 to the power of 15 multiplied by your 1.12 times 10 to the power of negative 27. So n photon. And that would get you 1.06 times 10 to the power of negative 11 kg ms negative. Sure, it's not so weird. Yeah, light got momentum there, cute or not? Okay, so if you arrive at this, if you use H over lambda, you will get first mark already. Let's see one. You remember to multiply by n now. So quantum physics, right? Because we are learning at the beginner level, the equations are all very nice to use. The concept's a bit mind-boggling, but you can just use the equation. Right, and finally, force exerted on the surface of light, by the light. You know how once upon a time from Newton's second law, force is rate of change of momentum. So when the light is hitting the target, the metal target here, it has a momentum of 1.06 times 10 to the power negative 11. And then it says in this question here, it is completely absorbed. That means the momentum will finally be 0. So completely absorbed. Momentum equals 0. So this is final, this is initial. So the change in momentum is 1.06 times 10 to the power negative 11. How long did it take for this many photons to hit? 1 second. And the time gap that we're using is 1 second. So in 1 second, we have this many photons with this much momentum hitting the metal surface. So I get 1.06 times 10 to the power negative 11 Newton. Such a big force. So measurable. So yes, although the light does exert a force on you and me when we stand outside under the sun, or maybe the light is pushing your face from the screen. Wow, light is pushing my face, giving me a face massage, but actually you don't feel anything. Negative 11, feel what? It's very small. So it's just hilariously small for our scale, because to us, it's very small. But for an atom, for a very small particle, this can be significant. Okay. So completely absorbed, the final momentum is 0. All the land energy is gone. Okay. Next one. Teacher, got momentum, then there's this question they like to do, the collision one. Can ask again. Because sometimes the final momentum is 0 because all the light is absorbed. But sometimes the final momentum is not 0. How does that look like? We're going to look at page, let me see, page 11. Okay, so remember these questions, they may look intimidating, but the question gives you a lot of hints because it's new. So a lot of help, not like other chapters. Okay, so here, what we have is a photon of wavelength 6.5 times 10 to the power negative 2 incident on an isolated stationary electron, as illustrated in figure 8.1. Okay, so we have a photon is going to whack the electron. Okay, you can treat this photon as light particle. Okay, going to hit the electron, and the photon is now here. I noticed that the wavelength has changed from 6.5 times 10 to the power -2 to 6.84 times 10 to the power -2. Seems like lambda has decreased. And you know, E is hc over, no, lambda has decreased, but lambda has increased. 6.5 and 6.84. So when lambda increase, it means energy of photon decrease. Makes sense, right? Energy, the photon loses energy after collision. After incident or collision. I want to put collision here in big inverted comma, because after a while we just call it incident. Before the incident, after the incident, you know. All right. So this is called photon deflection. The light can actually change its direction of path if it collides with particle. Okay. And the wavelength is given. Calculate for the incident photon. So incident photon, this one. The momentum and its energy. Okay, momentum. P is equal to H over lambda. 6.63 times 10 to the power -4. We have lambda 6.50 times 10 to the power -12. So let's throw inside. So you will look at this one. You see all their answer is 3SF. So your answer should also be that. Yeah. 3SF. This one, 3SF. So follow the lead of the question. In quantum physics and in particle physics, because we're dealing with things that are very small, we need very sensitive measurement. So sometimes 2SF is not enough. So follow the questions guide. Okay. So right now, this one is 3SF, this is 3SF. And finally, you write these two. You get 1.02 times 10 to the power -22. Okay, this is better if you like. Follow the sequence. I actually need to go back and check if I follow the sequence. I'll do that later. Okay, 1.02 times 10 to the power -22 for one photon. And that's 2 marks. You show the substitute, the equation, and the substitution is 1 mark, and the answer is 1. Beautiful. Energy. Okay, to find energy, E is hc over lambda. So 6.63 times 10 to the power -34, 3 times 10 to the power 8. I can almost guarantee you will use this equation in your exam, just don't know which chapter only. Lambda is 6.50 times 10 to the power -12. Okay, so if you press your calculator, you will get 3.06 times 10 to the power -14 joule. Because still 3SF. This one is actually 3.00 lah, but let's use. Okay. This is also a nice bonus because it's also 2 marks. See, 4 marks already. So equation, substitution, 1 mark. Final answer, 3.06 times 10 to the power -14. Next one. Sure, this one 3SF, this one also 3SF. Okay. The reason is because lambda is given to 3SF. The physical constant, normally we let it be 1, but we look at the wavelength, the data given. Data given to 3SF. But the only data that we actually have is the wavelength. Everything else are just physical constants. Okay, next. The angle theta, wow, good thing don't have to do resolution, right? Resolve vector, horizontal, vertical, very nice. So the only thing they say here is the angle theta through which the photon is deflected is given by the expression this much, where delta lambda is the change in wavelength of the photon. H is the Planck's constant. Okay, I'll just describe the equation for you. C is the speed of light in free space. Calculate theta. Sure, can just substitute, can. You delta lambda is h over MEC 1 minus cos theta. Looking for theta, right? So delta lambda here is a change in wavelength. So what we have here is 6.84 minus 6.50 times 10 to the power negative 12. I guess I'll just continue. Multiply by mass of electron. 9.11 times 10 to the power negative 31. Speed of light 3.0 times 10 to the power of 8. Divided by 6.63 times 10 to the power negative 34. 1 minus cos theta. So I guess we can find cos theta and subsequently theta. 0.34. You need to know where the equation come from. Nope, not in your syllabus. It's the electron deflection equation. But if they give you, just use. So I got my cos theta is 0.8598. Okay, written to 2SF is 3SF is 860 lah. And now cos inverse the answer. It will be 30.7. Okay. So the angle deflection is around 30 degrees. 31. Let's use the equation. Okay. Last part. Use energy considerations to suggest why delta lambda must always be positive. Okay, I'm going to start with this one. Delta lambda is always positive means the deflected, means after the interaction, deflected photon has longer wavelength. Longer wavelength means less energy. But why does it have less energy? Well, because remember, they share the energy. So you have maybe your photon. This one is short wavelength. High energy photon incoming with a sleepy electron. So this one is HF. Or even better, HC over lambda. Lambda 1. Okay. So after they collide, what will happen is some collision happen, bing bang boom. This wavelength now is longer. So this energy of photon decrease. It's less. Lower energy. This energy of photon is higher. More. Who took the energy away? HC over lambda 2. Lambda 2 is always bigger than lambda 1. And the electron, electron is going to shoot in this direction, somewhere down this direction to conserve momentum, remember? So the horizontal momentum is conserved. The vertical momentum should cancel out because the initial setup, there's no vertical momentum. So the electron must travel here, taking away some of the energy. Some E photon given to electron. Okay, And I know the electron will move here in this direction to conserve vertical momentum. Because we resolve this one this direction, resolve this one in this direction. They kind of cancel out. Can I find momentum? Can. P is H over lambda. You have lambda, you have momentum already. You can resolve. So this is in this direction. Direction of the electron is to conserve vertical momentum. Okay, we're gonna just throw all of these together into your 3-mark explanation. Okay, starting by the electron, because we have to rewind and explain why the energy of photon is less. So you can say after the incident or the interaction, the electron has some energy from, where does this energy come from? Because we cannot create energy, right? So taken from the incident photon. Because they say use energy consideration, cannot talk about momentum, okay? All right, so from here, I just need to say electron have some energy. And the second thing I will say is from conservation of energy, the photon loses energy, or the photon have less energy. And because of this, photon will have a longer wavelength. Longer wavelength. And delta lambda is positive. Okay, so 1 mark is when you mention electron has some energy from the photon. The other mark is when you bring out the conservation of energy. Photon will have less energy. And the final mark is when you say photon will have a longer wavelength. Also, it has to be from the incident photon. Electron has some energy from the incident photon, not just from nowhere. The trail of evidence of the energy transfer is very important in our discussion. We need to know if there's extra energy, where it comes from. If some energy is missing, where does it go? Cannot justify means you obey one of the greatest. I mean, that means something is wrong, because we have to obey the conservation of energy. If not, you can create energy, it's like magic, you know. It's like currently my pen is not on fire, but I can create energy and then light my pen out on fire, just like that. I got one. How? Unless we are in Harry Potter universe. Not gonna lie, it would be quite cool. All right, so if you want to try a similar question around diffraction, it hasn't come out since this year, which is 2015. Will it come out again? I don't know. Very anomalous, very strange, but must discuss in case. So you can try page 12. That's a similar question. May, June 15, paper 4.2, question 6. Okay. This one is electron diffraction. And another similar one would be page 10. May, June, no, not May, June. ON 14, paper 4.3, question 8. Pressure of light. Got force, sure, got pressure, right? So similar to the two questions that we've discussed just now. We can try both of this. Let me go and look around a bit, see if there's any strange looking question. Okay, a must do question if you haven't done it yet. But I have chosen it to be recorded, so you can go and watch this on the channel. It's ON 19 paper 4.1 question 11. If you haven't done it yet lah. And also page 19. These are the last two is photoelectric effect. Pretty sure I've asked you to do it. But the questions are getting repetitive, more or less. So I just want you to have a different experience. This one is evaluating your work function. And this one is discussing changes in E photon, or rather changes in frequency and intensity. This can be confusing for some, but you can try out the question first. So don't watch the recording, you try first. See whether your idea is correct. Check the mark scheme. If not okay, then only spend the time to watch the video. Of course, the recording takes time. Okay. So I think that's it for the Broglie and also the photoelectric effect and the wave particle duality. Quantum physics is a very, very strange field. Okay, there are a lot of things that we don't know. We don't really know why electron behaves this way. We just know it does. We don't really know why light is like this. We have some hypotheses, but they're all still work in progress. So we don't really put it inside the textbook because it's work in progress. And because it's work in progress, there are bound to have some changes, bound to be some changes. Okay. So, yep. So since we have a few minutes, let me go and farm some questions. But next week, or rather, let me see. Next week is going to be May. So what is our class hour count? Okay, so we have 5.5 hours left. And we did 2 hours on Friday. So wait, 1.5 hours on Friday. So Friday is 1.5 hours. And today, which is 28, and Friday was 25th. It's 2 hours. So minus 3 and 5, 3.5. We have two more hours left. And I am thinking that May has 4 weeks, 4 Mondays. So we'll find a place lah. But May is my GG month because trials and marking. So I'm guessing somewhere towards the end, like this one. But if you need to, we can find time. Yeah. We see how lah next week. But I owe you 2 hours to carry forward. Okay. Say first, scared I forget. 2 hours to carry forward. Yeah. All right. Or if later cannot find time or don't need to, then just prorate and deduct from the last month. Cool. I very chill one. I just found out from different because do you know, okay lah, now we sembang first. Do you know that this very interesting website that's been trending called the Malaysian Pay Gap? You heard of it? Actually, very cool one. If you want to know like how each sector is like, I don't know what you want to be, private tutor, crypto manager, marketer, Grab driver, veterinarian. You can actually see how much people earn, like kindergarten. Very sad. Yeah, and then I joined their Discord. Yeah, so you can I mean the salary is one thing, but sometimes I look at this one, like this is private tutor, which is technically my job right now, right? Because I'm teaching you, but what time is it? 11 o'clock. I got no life, my dudes. So this teacher is also probably no life lah. Do I like to hang out with students? Yes. But I don't think you want to pay me money so we can talk about music, sports, and be part of their life that much lah, right? And this one is crazy, man. We teach tuition 9 hours a day. My max cap is 6 hours, including my college class. Like I would not teach more than 6. I would die. My brain I will start teaching wrong physics. So I'm not sure how he does it. But yeah, it is a lot of money. And then after that, I went and looked at the Discord channel, and there were some tutors saying that, it was about their difficulties. So it's very interesting because people generally don't talk about how difficult their jobs are. But hey, Malaysian pay gap. So you go and look it out and like, hey, maybe I'm interested to be a 3D artist. I don't know, whatever. Consultant surgeon. 120K a month. What? Okay lah. It's interesting. Please don't spend too much time there. It's an interesting way to look at different sectors. Because what I find more interesting is actually if they write long about what happened in their career, it's much more interesting to me. And even more interesting to hop on the Discord and see them talk more. But yeah. So try out these questions. We're going to end quantum physics the next class, which is about X-rays. And we're going to do quite a lot. So we'll talk about the production of X-ray, how to create good X-ray image, do some calculation, and then talk about CT scanning, which is not X-ray, energy level first. Then we start a bit of X-ray. Yep. So I will put the link. I don't think we need the link. We'll go Instagram and find Malaysian project. Anyway, next week, we'll do the hydrogen atom line spectrum. This subtopic can combine with astrophysics one. So we'll spend maybe 1 hour doing it. And then after that, we'll start a bit on X-ray. Okay, let me ask you, you want to do X-ray, medical physics, and just continue to medical physics everything? Or do you want to follow the syllabus and do radioactivity, study nuclear bombs? Okay. 2 or 3? Why? A or B? And medical physics? You want to study about medical physics. Okay lah. So we'll do medical physics, meaning we park the radioactivity to after medical physics, okay? So we'll do med physics, radioactivity, and then we'll do astro. Because you need to know radioactivity and medical and a bit about X-rays to talk about astro. Astro is a very nice dessert chapter to wrap up your entire 25 chapters of physics. You came a long way. Okay lah, Ken, I'll see you next week. We'll start with the first one, which is X-rays. Okay lah, take care. Bye-bye. Good night. Any questions? Welcome. You can always message me on Discord.